All right, so your lab test tomorrow, Wednesday. Most importantly, please go to Williams Small Center, not LSB 102. If you go to the wrong place, too bad. There will be no test for you to complete. Please go to the right room. 106 and 108. No seating plan. You can just sit wherever you like. Actually, sorry, that's not true. 106, we'll try to fill it out first, and then we're going to arrange some of you to 108. Okay, so 106, please. Okay, but I'll be there to guide you. So my advice will be for tomorrow, you got to make sure you're proficient with the concept that's actually covered in Lab 1 and Lab 2. And I think especially trying out the 424 test I gave to you will be very useful. If you can, try to redo it once more with some time constraint before tomorrow. I'm pretty sure that will help, right? So other than that, we'll see how that goes tomorrow. Okay. Any questions? Yes? I would say it's really around. Tomorrow's, there will be, of course, there will be some difference. There might be certain part that might be a little bit easier. There's certain part that might be a little bit harder, right? Yeah, I would say it's roughly around the same, but not exactly the same, of course. Okay. Yeah, again, my advice would be, so my advice, redo the 424 version and also review the concept in the, not OOP, the math review as well. Okay, just got confused with another course. Yes, question?
Yeah, so the event B summary document, is that going to be ready on our machine or no?
The event B summary, yes, it's going to be on your desktop when you log in, so you don't need to worry. I believe I also said in the test guide, if you want to print out a fresh copy, like a paper copy by yourself, that's also fine. But you got to make sure it's kept as clean throughout the test. Don't take any sketch notes on your event B summary document if you choose to print it out and bring to you. Okay?
And for the evaluation of the machine and the context that we wrote, are you going to evaluate by the script or it's going to manually be graded by the TA?
So mostly it will be graded by the TA. So TA will actually judge to see the logical correctness. Also, we're going to see if all the proof obligation will be proof automatically. You don't need to touch the manual proof part since we didn't cover. You don't need to touch that. But everything you specify as a machine and the context altogether, you should really get green for all the proof obligation. You should. All right? Yes? Basically the same format, basically the same. But of course, sometimes may not be exactly prescriptive. I might say you may want to define a relation, short, that might be quite explicit. Sometimes I might say you may want to define a mapping between two things. That should be a function, right? Something like that, yeah. Yeah.
So you said we don't have to touch the manual post tactics and stuff, the auto post tactics.
That's correct.
Does that mean that all the proof obligations are going to be dismissed properly, or do we have to do that?
Yeah, so tomorrow you're going to create a project from scratch, but you don't need to touch any setup. You don't need to worry. So the model solution that we have behind the scene, we already tested. Everything is going to be proof without adjusting any tactics. Yeah. Mm-hmm. Yes?
Will it be a better strategy if, let's say, we found an axiom in the context that we think it's pretty hard to achieve and we're not sure, or let's say an event on the machine, that same thing, right? Is it better to perhaps skip it or leave it empty for compilation purposes, or is it better to give it a try?
It's a good question. I would say if there are certain axioms or theorems that you're not exactly sure what to do, let's say you're totally clueless, for example, right? I would say either you simply don't put anything about it. For example, that should be axiom 3. You simply don't put axiom 3 in your machine or context, right? Or you can put something there, maybe just put true. At least that will compile, right? At least, right? Yeah, go ahead. There will be some to an extent, but we'll see how everybody does, right? And then we'll try to be, just for that part, there may be a little bit more lenient. Okay, we'll see. Okay, yeah. Don't take my words for that just for now. We got to see the grading scheme, right? Yeah. Okay, please, final one. We're going to cover some stuff, guys. Okay, go ahead, yeah. So say it again, so I didn't hear.
The prover doesn't pass, right? Can we just turn everything into an axiom?
No, you shouldn't really. That's a very smart, but you don't want to do that, right? So I think in the test, you will be very explicit about certain things should be declared as axiom, like AXM, like what you saw in the 424 test. Some of them will be THM, like a theorem. You should declare that as not. You should declare that as theorem, right? So you'll be explicit instruction about those parts, right? All right, guys. Let's now continue, okay? And then we'll see. Right, so I think today what we're going to cover, some of them might also be very useful for tomorrow as well, I'm pretty sure. I wouldn't tell you which part, but I'm pretty sure, at least one thing. Okay. From last time, very quickly. Okay. So we spoke about the relational operator, especially overriding, I'm pretty sure this one is useful. Okay? And I can also give you one hint. Review the transfer events for lab 1. Okay? That's good hints, right? So exactly why, don't ask me, but you may want to review the events. Okay? Overriding is going to be very useful, so you may want to review about its definition. So I'll leave that to you. And then we talk about algebraic property for overriding as well. Okay, so this will be a very nice property for you to know. All right. And then we spoke about functional property, right? So basically, functional property simply means for the same domain value, we may only map to at most one value in the range. At most one, cannot be more than one, right? That's a functional property. And we say that every relation is a function, but some relation, sorry, let me say it again. Every function over here should be a relation by default. However, some relation over there may not be a function. How do you show that? You got to show witness in the relation that's going to violate the functional property, right? And we spoke about 2 ways to actually understand the property. Either the standard way, or you can apply control positive to really see that. You can go either way. Okay? Let's say, for example, if somehow you have to write out the functional property in the test or even exam later, you can feel free to write either way. Either way is considered correct. Okay? Whichever way you feel more comfortable. All right, so this part here, you can definitely review about the partial versus total function. Again, as long as a relation satisfies the functional property, that is considered as a partial function. So partial function is the most general form of the function. Right? So that's why we got a partial function right here. And then there is a special kind of partial function called total function, right? Which means the domain must be exactly the same as the first set, which is S right here. Right? So that's the difference. So another hint for you. So maybe sometimes if we kind of ask you about to declare what should be the type of certain variable, if you are asked to really choose the most accurate one, for example, you want to decide whether this will be the most accurate or this one here or this one. To really decide which one to really go, you want to think about what kind of a property it is supposed to satisfy, right? You should really find the hints in the problem description, okay? That's also another hint for you. And then I just spoke about some example, right? We'll see more example today. All right, and then we just talk about accuracy, right? So sometimes you want to be as accurate as possible, right? So think about it in this way. So all 3 over here will be correct, but we say that this one here is the most accurate, but this one here is the least accurate. Even though it's the least accurate, but it's still correct, right? So you want to have that kind of degree of accuracy. All right, so let's now move on, okay? So first of all, let me just clarify about the functional application versus relational image, right? We do want to know the difference, right? So just remember this diagram here. So we have, let's say we have a function here. Let's say just partial function, satisfying the functional property. And then we have the relation, which is strictly larger, right? So that's why we say anything that satisfies the functional property should be a relation automatically, but not vice versa. Okay? So having this, let's now talk about something useful. Okay? So let's say we have f. F is simply a partial function between 2 sets. Let's say this is S, and this one here is a second set called T, right? Partial function. That means, for example, you shouldn't really have one that's mapped to both A and B at the same time in the same relation, right? You shouldn't have that, right? So this is a nice example for the partial function, okay, which is good, okay? And then I just want to talk about something quickly here, okay? So let's say for this particular example, when we say F, okay, F is a relation, first of all. So when we say is functional, which is going to be either true or false. So we fit in f as the input into its functional, checking to see if there's a function, like a partial function, right? And then we want to also check to see whether the domain is actually part of the 1, 2, and 3, right? And then we got 2 cases. So we got the domain of f. Partial function simply means it can be a proper subset or equal. And then we got S, 1, 2, 3. Right here. All right, and then let's now review the 2 possibilities we had the other day, right? So that will be useful for today. So let's say when we talk about just this part right here, okay, let me move this one here a little bit upwards. Right here, okay? So there are two possibilities. Possibility number one. Let's say the domain of F is a proper subset of 1, 2, 3. That could be one possibility. Or it could be that it is exactly equal to it, right? We are basically splitting between this case and also the equal case. And then this one here, the domain of F is exactly equal to 1, 2, and 3. All right? Specifically for this one here, when the domain is a proper subset of 1, 2, 3, what does that really mean? That means there's at least one value from S where it don't have the corresponding range value. It's not defined in the function. At least one value from S, right? So this set here is something we call S, right? The same S right here. One value from S that does not have a corresponding range value. That does not have the corresponding range value. This is something we know pretty well, right? It's even like a review. Okay? And then this one over here, of course, every value from S has the corresponding range value. Okay? That's what we know. All right, so now let's take a look at this particular function, right? Is this function total? No, because 3 and 1, you're missing 2. That means at least one value from there, which is 2, does not have the corresponding value in the relation, right? You can see 2 here simply has no corresponding range value. We don't know whether it's A or B. It's set to be undefined. Okay, let's see this. So the exercises we want to do. First of all, let's start with the relational image, right? Because F over here is actually a relation. At the same time, it's also a function. So we can actually do both. But so we're going to see applying the same F either as a relation or as a function, what kind of result is it going to give to us? So let's see the contrast over here. Let's do relational image here. So if I say F is a relation, right? So here we are treating F as a relation. Treating F as a relation. As a relation. Okay? And then we are doing relational image. Okay? So now the value for this one here, what would that be for 3? Just A. Agree? Just A. And this one here is also part of the domain and also got B. Notice that the return value here is more like a set, right? It's not a single value. Okay? And you can see this one here. 2 is a member from S, but 2 is not a domain of F, right? So 2 is a special value here. It is in the first set, S. However, it is not a member of the domain of F, right? You can see that, right? So now what would this be? Empty, right? So you can always get a return value from the image, even though it's an empty set. Okay, that's important. So now what we want to see is, now F can also be treated as a function. In which case, we're going to apply all the 3 values again, but we're going to see the contrast. You're going to have like a different consequence. That's something I want to kind of indicate to you. Okay. So we talk about relational image. So this part here is about relational image. Relational image. Okay. Let's talk about another operation, which is functional application. You can think about the F that we are talking about is really somewhere over here, right? It's both a function and a relation. That's why we can apply the 2 operators to the same F, right? Let's now just write it down. How do you actually write a syntax for a functional application? Exactly how you did it in a math class, right? So you will simply say something like, let's say F of 3, F of 1, F of 2. All right, so now here, be very careful here. You can see the subtlety here. The input to the relational image is a set. Because a relation in general, a domain value may be associated with more than one range values. So that means this can be a set, right? You can pass multiple value over here. On the other hand, here, for functional application, you're given just a single value over here. And given a single value, you should have just at most one range value that's defined, right? So this is a set, and this part here is going to be a single value, all right? So let's see what they are, okay? F of 3, A. F of 1, B. What about F of 2? Undefined. You cannot say empty set anymore, right? That's the point I'm trying to make, all right? Undefined. Here, mathematically, you may have seen this symbol here. It's called the button symbol, right? Undefined. Okay. Undefined. Yeah, sometimes people treat this as false as well, but undefined is also possible. Okay. All right. So let's see. Let's emphasize the point again. You want to see this one here is simply empty set, and this one here is undefined. So it depends on whether you're passing a value that's in the domain of the function or relation. Okay. So based on this, I'm just going to mention something here that you want to be aware, just in case it might be useful in rodent. Okay. So let's say in rodent. So let's say, for example, if you have f, and then you say that's an integer relation to integer, right? This is a relation between integers, okay? And whenever you're writing some expression here, let's say you got some constant c, and of course, the only thing you want to make sure is c is an integer, any integer value, okay? We say that this particular expression over here is always well-defined. You don't have any associated proof obligation with it behind the scene. You don't have, right? Always well-defined. In the worst case, if C is not in the domain of F, you just return empty set, right? It's always defined for some value. On the other hand, if you declare, let's say G, to be a function. Let's say it's a partial function between integers, like that. All right, let's say a different function, okay? And then if you say G of C right here, and again, we are making the assumption that C, let's say a constant, is an integer. If you write down this expression here, there will be an additional proof obligation rodent is going to generate and try to prove, which is C should be in the domain of G. Otherwise, it's undefined. Okay? Let's say you're doing this under the context of some events. You got to make sure there's a guard to say C is in the domain of G, something like that. Or there could be some axiom. Okay? Okay, so this one here, not always well-defined. And the way, so there will be one proof obligation generated, which will be C is in the domain of G, in order for that to be defined, right? So that's a subtlety you want to watch out for. So it really depends on what kind of type you declare the variable to be, right? If you're only using relational image, that's okay, right? The worst case is just return empty set. On the other hand, if you're using functional application, then you might have some undefinedness, right, for the value. All right, question? Okay. Let's now do some, just before I do some exercise, let me just say one more notes, right? And then we can do some exercise, a little bit more informal exercise. Okay, so let's now talk about the cardinality quickly. Cardinality of relational image. Okay, like that. All right, so let's say I declare R to be a relation. Okay, and then if I say R is also a function, it is possible, right? What does that mean? That means if I try to apply the relational image on certain value, it's guaranteed the cardinality of the set of value that's returned should be less than or equal to 1, at most 1, right? That's something I want to mention to you. So if I try the following, if I try R relational image, and then I'm trying to put a set right here. Set over here, and then I'm putting some value, let's say little s. And here, little s is a member of capital S. S here, right? And now, if I want to take the cardinality of the return set value, right? The return value is a set. And that one should be less than or equal to 1. Right? And let's now try to split the cases. What does it really mean when it's equal to 1? What does it really mean when it's equal to 0? Cannot be negative, right? What does it really mean when it is equal to 1? What does it really mean when it's equal to 0? Should be a simple property observed, right? Okay, I will let you try. What does it really mean when it's equal to 1?
So when it's equal to 1, which means that the C is in the domain of this relation R.
Yeah, except you meant S, not C, right? Okay, good. Okay, very good. So that means the little s is in the domain of R. And if that's equal to 0, that means you cannot return, you just return an empty set, right? So that means S is not in the domain of R. Right, so just adding cardinality just to express different properties, right? Any questions? Okay, if all good, let's do this little exercise here. This one's interesting. This is what I call the modeling decision kind of question. We got 2 of them for today. So this is actually very nice. This will give you some flavor about once we get to the bridge controller, we're actually going to somehow use the math to interpret some modeling decision. So that's really the value of this course. We're not only just doing math, just manipulating symbols, but we have to do something useful. Okay? Let's now read this together, okay? And then we'll talk about some different modeling decision. Okay, let's say we have some company and we want to keep track of where the employees are. Okay, so they could be in Zoom A, maybe floor 23, right? Let's say the location could be LSB 105 or LSB 106, right? Just a string, okay? And then to really do this, employee simply wears some badge, exactly, just keep track of where they are. Employee may be on the company premise, or maybe employee may be outside the company premise, right? Things like that. And I'm just going to talk about different modeling decision with you, all right? Right here. Okay, let's now still focus on just this part here, okay? So let's say we got 2 carrier set. Let's say we got a carrier set called employee. All the employees in the company, right? And also we got location, all the valid location in the company, right? 2 carrier set right here. So we have this tracking function, or tracking relation, whatever you like to call it. Let's say tracking relation. That's the most general way to say that. Okay? So now, is it appropriate to really model the where is as a relation between employee and location? All right? I like the answer, no. Okay, that's part 1, right? And part 2, why? Go ahead, Iago.
It would be appropriate to define this as a relation because it doesn't make sense for an employee to be in 2 places at the same time.
Yeah, exactly. Because relation will allow the domain value to be associated with more than 1 range values. Good? So we might have, for example, okay, the answer is no. The same employee to location number 1, maybe in the where is location. And also the same employee in another location, maybe also in where is. Okay, not appropriate. How can the same person be in two locations at the same time, which is allowed by relation? Okay, now, we know that relation is not good, so let's try a function. Can a total function work?
Yeah, no.
I heard yes, I heard no, okay. Okay, think about what's really the difference between total and partial function, right? If I say total function, what does that mean?
That all the employees will have to work.
Yeah, okay, so does that make reality sense? For example, let's say on campus, do you expect all the students to be on campus at any time?
No.
Some of them might be at home, some of them might be traveling, right?
But if the system is keeping track of its employees on the premises,
Yes.
I'm assuming all the employees are already on the premises, so we should know the location.
No, you can think about where is over here is more like a variable. As the system evolves, you also have to change the mapping that's inside the function, right? You gotta add some pair, you want to remove some pair. You can think about every time employee goes into the company, we're gonna add that pair into the relation or the function. Whenever an employee leaves the premise, you gotta remove that pair, right? So total function here may not be the way to go, right? Good. Okay. All right, so total function is not good. Okay, also no. Because some employees may not be in the company premise. All right, so our final decision here might be maybe just a partial function, right? Okay, so that will be the way to go. Yes. So this will allow us to maybe have some undefined value for certain employee because they're simply not on the premise. All right. It's a simple exercise here just to kind of see the difference between relation, partial function, total function. But we're going to see more today about under the function category, you also got injective function, surjective function, bijective function. That's something we'll see today. All right. Yes, question?
To my understanding, the first line there, like the E1,
Uh-huh.
the EL map to L1, you represent the order pair, right?
Yes, that's correct. Yeah, so I think in Rodin, I'm pretty sure you know that symbol, right? It's about maps to, right? So I think, so it's like an order pair. But on the paper, you can either say this way or you can say maybe E1, comma, L1.
Yeah, and however, for the symbol on the right, isn't it supposed to be using the member of where is, because like now it's like E1 map to L1 map to where is.
I'm just saying this pair is in the where is. And also this pair is also in the where is.
So when we say some element is in a set, shouldn't we say it's a member of it?
Oh, I agree with you. Yeah, you're actually quite right. I definitely don't mean to write that. Yeah. I agree. Absolutely. Good. Awesome. Okay, I hope we can see the issue, right? What I wrote before wouldn't even type check, right? So you definitely want to say this pair here is a member, and this pair here is also a member. Yes. Good. All right, let's now move on. So I think the final bit we need to talk about for the math review is to subdivide the function into different category, right? Let me just do a little bit preview about what we're going to talk about, right? So let's do here, and then we'll do examples, just to verify, to reinforce the understanding. So we have functions. And let's now do again a table, like a preview. Okay, so one dimension is to see either it's a partial function or total function, right? Either it's a partial function or it's a total function, right? So if you remember, partial function is a bit like that, right? And total function is a bit like that. Okay, just remember. Okay? Because somehow the symbols will actually be derived from the different dimensions you were talking about. Well, we'll talk about it. So we're going to first of all talk about a property called injective property. And the injective property is more about the domain value, which we'll see. Okay? It's more to do with the domain. And we're going to talk about something called the surjective property. Surjective. That one there is more to do with the range. Okay? And then we got another thing called bijective. It's more like a combination of injective by surjective. Okay? So the third one here is bijective property. That one is more like a combination of both. So we got a domain and we have the range. Okay? Of course, we'll get to the mathematical definition in a moment. Okay? So let's see the symbol over here. Okay? So when we talk about partial, so we got partial, we can say we got a partial injective function. We can have a partial surjective function. Okay? But first of all, we don't really have anything called partial bijective function. Whenever you say bijective, it's got to be total, always. Okay? So the only thing that you don't need to worry about is over here. So this cell here is not applicable. You don't have any symbol for that. Okay? So for this part here, you can also call that a partial injection. And this one here, you can also call that a partial surjection. But you don't say it's anything like a partial bijection. There's no such thing, right? Just not applicable. How do we write a symbol? Okay. If you start with the partial function, which is something like this. Okay, partial function. And injective property is more to do with the domain. So you're just going to add a tail right here. That's a partial injection. Just remember, partial property, injective property is more to do with domain. So we just add a tail. Okay? And then what about surjective? It's more to do with range. We're going to add an arrow. So we start with the partial function right here. And then we're just going to add something on the range part. Domain on the left and range on the right, right? So that's a partial surjection. Okay, similarly, we have total. So we have total function here. And then injective is to do with the domain. So add a tail. And we have the total function here, and surjection is more to do with the range. So put it here. Okay, all good. What about bijection? You don't really say total bijection, because when you say bijection or onto function, so one-to-one correspondence, they already imply it's total. What you have is you got some total function here, and then you have to worry about the property in both the domain and also the range part. So you're going to put the domain and also the range. Okay? Symbol, right? Kind of logical, right? So that's why I want to kind of spend some time with you about this. All right, we're going to look at each one of them. We're going to look at injective first, and then we're going to look at surjective, and then we're going to look at bijective. Yes, that will be the order. Okay? Why don't we look at injective first before the break? All right, injective function, right? You can also look at the slide, just combine them together, right? First of all, let's look at the definition, okay? And you can see the definition here looks a little bit like the same pattern as the functional property, right? A little bit like, but it's not exactly the same, okay? Just for your reference, I'm just going to put a functional property along the side. So just remember, they are not the same thing, okay? So just remind you, if you recall, we got for every S, T1, and T2. And then we say S should be a member of S, and also T1 should be a member of T, and T2 should be a member of T. That implies if ST1 in F and also ST2 in F, that simply implies T1 equals T2. Right? So this is the functional property we learned earlier. Okay? This one here. And its interpretation, you can look up the notes from earlier. As a functional property. And the one we are learning right now is called an injective property, right, in the yellow. Okay, right here. But I'll show you some critical difference quickly. Okay, so this one here is the injective property. One thing you should note, in order to state the functional property, you have to use one domain value and two range value, right? T1 and T2 are from the range. And S over here is from the first set. You want to use a one first set value and two second set value. On the other hand, to really specify about the injective property, you will need two values, S1, S2, from the first set, and also one value T from the second set. All right, that's the difference. Okay, but let's now look at this interpretation over here. Okay, what does that mean? If you actually have the same range value, first of all, you can see the T here and also the T here. So this one here, let me just write maybe above. T and T, they are actually referring to the same range value. This is saying if you got S1T and S2T in the same function, then S1, S2 must be the same domain value. What does that mean? That means you cannot really have the two distinct domain value that map to the same range value. I'll write it down first, and then we'll see some violation witness. Okay, let's write it down first. This one simply tells you that you cannot have two distinct domain values mapping to the same range value. Just notice about the distinct and also the same, right? Just notice that. So the same and also distinct. All right. Let's see one violation right away. How do we disprove that some function is actually not injective? How do we show that? One very easy way to show that, let's say for example, if I have, let's say something like this, 1b and also 2b. It's a simple function because 1 is only mapped to one value and 2 is also mapped to one value. We know that it's a partial function, right? That's something we know, right? And then, is this injective though? Turns out it is not. Let's see exactly, right? So let's now plug in this value here, these two pairs into this implication. That's exactly how it will fail, right? So now, if you try that, so first of all, S1 and also S2. You can think about this is T and this is T. So 1b is in, of course, I can say this is F. Okay, 1b in F and also 2b also in F. This whole thing here implies the domain values are the same. 1 equals 2. True implies false. We got false, right? It's a violation. All right? So this one here is going to give you false. So whenever you want to see if something is an injection, you want to make sure there are no two distinct domain values mapping to the same range value. But we'll see example. Okay? Let me see one more thing, and then we'll actually talk about the example. Let's look at also this part here. Just this part. And then since it's implication, you may also want to apply contrapositive to see if that can give you more insight. Let's take a look, okay? So I would say, let's now try to do, let me say star, star, okay? And then star, star over here, I'm just going to apply contrapositive. All right? So this one tells me S1, S2, not the case. S1 not equal to S2. S1 not equal to S2. Implies not the case. These two pairs exist in the same function at the same time, right? It is not the case that S1t in F and also S2t in F. It cannot be. Either one will be fine, but not both. Because if both of them are in the same function, whereas S1 and S2 are not the same domain value, then it will violate the injective property. So try to look at maybe these two implications, one at a time, try to see if that can give you some interpretation. Okay? And again, if in the actual test or exam, if you are somehow required to write about the injective property, you can write either way, okay, to see which one makes more sense to you. Okay, let's now do example, okay? I would say injective might be the most complicated one to really understand, compare with surjective and bijective. So we're just doing the harder thing first, which is good, okay? Why don't we just do just this example here, and then we'll take a short break, and then we'll do the other half, okay? Just this one here. All right, so for this one here, let me just maybe let me just do this. Okay, let me copy it again. Okay, right here. So let's first of all talk about partial injection, right? So the symbol is something we spoke about already, right? It's a partial injection. Okay? Partial injection means you have to check two things. Number one, in order to make sure it's a partial function, you got to satisfy the functional property, right? So you got to satisfy the functional property and also the injective property. Okay, so these are the two things we got to check. All right? And you can see we're using this subset symbol again, like last time. That means I'm specifying two things, three things in this case. I have this one here, this one here, and also this one here. So each one of these three are individual functions, or relations at least, okay? So now, first of all, is empty set, or empty relation, is it a partial injection? How do you think about it? Why is empty relation just a partial and injective function automatically? All right, remember it's an empty set here since we talk about universal quantification, right? So to really specify a functional property, we got to use for all. And also to specify injective function, we got to use the for all. And remember, for all is going to be satisfied automatically on the empty disclosure of universe. So that's why empty relation here is going to be satisfying both of them trivially. That's why empty relation here is a partial injection. Satisfy both functional and injective properties using for all trivially. And as also what your fellow student said, because he couldn't find any violation witness from the empty relation. So it will be satisfied. Yeah?
Isn't an empty set also, is it also a bijective function?
Oh, we'll get there, yeah. The short answer is no. Okay, we'll get there, yeah. All right, so let's see the next one. Okay, what about 1a here? Is 1a, first of all, is it a function? It is, right? Okay. Is it an injection? To really decide whether it's an injection, try to find. Can you find two different domain values mapping to the same range value? You cannot find that in this case, right? Because there's only one pair, so you don't have that concern. Okay? How about here? First of all, it's a function, right? That one, I don't need to bother you. Is it injective? You actually got two distinct domain values. Do they map to the same value? No, they don't. They map to distinct values, so it's injective. Okay? This one here I can write down quickly. Okay? So this one here, you can think about distinct domain values map to distinct range value. That means it is injective. Yeah, maybe you want to review the formal definition after class today a little bit more, okay? All right, let's now see this. Is this a function, first of all? This one here, is it a function? 1 only map to one value. 2 only map to one value. 3 only map to one value. So functional wise, it's okay. It's a function, right? It definitely is a function. This one here, it is a function. Is it an injection? Did you see the visual hints I gave to you? You see 1b and 3b. Distinct domain values, but they map to the same range value. It's not injective, right? But injective, no. Because distinct domain values 1 and 2 both map to the same range value b. All right, that's how you justify it. Right? Maybe you're learning, maybe seeing this the first time, or maybe it's been a while ever since you learned about it. So you want to look at the example here, also look at the definition that we saw earlier. Right? You still have time before tomorrow. Okay. All right, so let's now talk about the final one, and then we'll take a short break. How about this one here? So this one here, is it a function? It is a function, right? 1 only map to 1, okay? It's an injection. No, because there's different domain value map to the same range value for a similar reason. All right? So that's also no, okay, for the similar reason. All right, any questions so far? So far, we only talk about partial injection. That means we only check to see whether they will satisfy functional property and also injective property. After the break, we're going to see total injection. That means we're going to check one more thing about being total. Right? That's something we'll do after break. Right? So if you can please get your iClicker ready, and let's take a short break by taking attendance. Before we continue, one example, just one of your fellow students was asking me during the break. So let's say this. So if you got, for example, 1a and 2a, right? You can see here, 1 is only mapped to at most 1 value. 2 is also mapped to at most 1 value. So this one here is both a function, it's definitely a function for sure, okay? But it's not injective. Not injective because you got 2 distinct domain value, they map to the same range value. On the other hand, some other example we saw earlier, maybe last week, was something like this, right? If you look at something like this, if I got 1a over here, and then I got 1b, you can see this total different relation, right? This one here, is it a function? Not even, right? Because you can see the same domain value mapped to more than 1 range value, right? It's not even a function, okay? Okay, awesome. All right. Let's now go back to this example here, and then I might just create another page so that we can be more focused. There we go. Okay. So we now talk about partial injection right here. Okay. So I don't need this. All right. Sorry, total injection. That's what I meant. Okay. In order to see total injection, this is simple. We basically got to check 3 things. We got to check, number 1, about functional property. It's got to be a function. Also, it's got to be total, and also it's got to be injective, right? So now for each example there, we're going to look at a table just to help you, right? Let's put it aside. Let's say we got, basically, we have to check, number 1, the functional property. Let me just say prop. And then we also got to check total. And also we got to check to see whether the injective property is satisfied, right? These are the three things. And let me just number them. So let's say this is number 1, number 2, and number 3. Okay? Number 1, number 2, and number 3. And the one above, I'm going to talk about it specifically. Okay? And this one here. We can fill out the table together. Okay? That's how you decide. In order to be a total injection, all the three properties must be checked. If at least one of them is unchecked, too bad, right? Let's take a look at the first one here, right? And I would like you to look at that right here. Make it bigger. What is trying to say? Can you at least interpret what's being said? Not even to justify it. What does it really say here? The right-hand side is simply empty set, I know. You don't need to tell me, right? But the left-hand side is more interesting. Let me give you a hint, okay? Remember this symbol here. Right? This symbol here, when we say S and T, that simply means not a single relation. It's the set of all possible relations between S and T. Agree? Okay? It is the set of all relations between S and T. And this one here can be interpreted in a similar way. This one is saying the set of all possible total injection you can create between this set here and this set over here. All right? So that's very important, okay? I'll write it down. So this one here is the set of all possible total injection. So left-hand side, clarify. What about right-hand side? Right-hand side is telling me the set of all possible total injection for this particular case is empty set. That means there's no way you can even give me one total injection from these two sets. Can you see why? Go ahead.
Because there's less range values than domain values?
Yeah, something like that, exactly. Because somehow you got less range value than domain value, right? If you think about it just informally, right? Exactly, okay? So for example, if I wanted to be total, of course, I need to have 1, 2, and 3 in the first element. 1 something here, 2 something here, and also 3 something here. That's for that to be total. For that to be injective, I got to make sure, since all these domain values are distinct, I cannot repeat the range value. As soon as I repeat it, it's going to be not injective, right? So the best I can do is maybe I'll choose A here and choose B here. Now over here, for the third element, doesn't really matter which I choose, right? I have no choice. If I choose A or B, I'm simply going to create a witness about violation for the injective property. So that's why when you actually got this particular case where the range value are less than the domain value, you just have no choice to make any total injection. All right? Think about this inside here. That's actually very nice. Okay? So here, this will violates the injective property. All right, good. So first one, this one sorted. And let's now take a look at 1, 2, and 3. Okay, let's take a look at them, right, for each one of them. The first one. Is this, okay, let's just judge column by column, right? So for number 1, right here, okay? First of all, is it total? Yep. 2, 1, and 3. 1, 2, and 3. Total is good. Is it functional? Yeah, each one of them map to at most one value, right? You don't have any one domain that map to multiple range values. Is it injective? Yes, because you can see all the range value over here there are no duplicates, right? Awesome. So all 3 must be checked. So if you somehow want to justify it for the later two that they are not total injection, you got to tell me exactly which property they fail. We'll see. All right, let's see the second one here. Right here. First of all, is it total? Agree? No total, not total, right? Only 1 and 2. You're missing 3. Not total. Okay? Is it functional? It is functional. 2 only map to 1, 1 only map to 1 value. Is it injective? Injective, right? Because distinct domain value map to distinct range value. However, since it fell, one of them, so it's not a total injection. All right, that's why. All right, okay, final one. Let's say the final one here. Okay, let me use orange right here. Okay, is it total? Yeah. 2, 1, 3, total. Is it functional? Agree? Yeah. 1, 2 map to only 1 value, 1 only map to 1, etc. Right? Is it injective? Give me the pairs. That's gonna be the witness. 2D and 3D, right? So these are the witness. Okay, good. Again, since you violate one of them, so 2 and 3 are not total injection. So 2 here and also 3 here. Oh, sorry. Okay, awesome. So that's about injection, right? This might be the more complicated one to actually absorb. That's why I want to talk about it first. Okay, let's talk about surjection. Okay. Surjection is basically saying that the range of the function is going to cover the entire second set. That's what it is saying. All right. So here we're making the implicit assumption here. We're saying that f is a relation from S to T. And we say that S is also surjective if the range is going to cover the entire second set. We got some property that's very similar, which is about the domain. What if the domain covers the entire first set? How do we call that? Total, right? Okay. Just for your information, I'm going to write it down. All right. So here we got total of F if and only if the domain of F is equal to the first set right here. Okay. So let's talk about partial surjection. So partial surjection over here. So that means we got to check 2 things. Number 1, we got to check the functional property to make sure it is a partial function. Number 2, we got to check the surjective property. Right? 2 things to check. All right. And the first one here, okay, let's see this. We got this one here. Is this a partial surjection? Right? First of all, is it a function? It is, right? Okay. Is it surjection? Range will be A and B, which will match the A and B. So right here. A and B, which match the second set right here. So that's surjection. So this one here is good. All right. And then the second one. How about this one here? First of all, is it a function? It is, right? Okay, yeah. If you can somehow get it, that's good. I'm happy, right? So here we got, is it surjection though? So we got A, B as a range, also cover A, B, right? So both are example for partial surjection. But we didn't check to see whether or not it's total. We didn't check it. We only care about partial, right? All right, how about this one here? Is it a function? It is, good, thank you. And is it surjection? Not, because it only covers A. Does not cover A and B, right? It's not surjective, okay? So this one you can say that it is function, but not surjection. Okay, a final one here. How about this one here? This one is similar, right? It's a function, but you only cover B, which does not cover A and B, right? It's a function, but not surjection. Similar arguments. All right, so let's now talk about total surjection. Let's do the same table, just to be systematic, right? That's something you may want to put on your sketch paper, whenever you're solving some question. So again, let's now put it here. So we got, let's say we got 1, 2, 3, 4, okay? Let's say number 1, number 2, number 3, and number 4. Okay, we got 4 of them. Okay. So we got 1, 2, 3. Oh, let me just go a little bit better. 1, 2, 3, and 4. And then we're going to check 3 things. Okay. We're going to check functional property, total, and also surjection, right? So let's say we first of all check to see whether it's total. And then we check to see whether it's functional. And then we check to see whether it's surjective. Okay, let's check. All right, for number 1, right here. Is it total? Correct, right? We got 2, 1, and 3. 2, 1, and 3. Is it functional?
Yes.
It is, right? Good. Surjective? A, B, A, right? A, B. Okay, so overall, good. It's a total surjection. Awesome. And then let's look at the second one here. The second one, okay, let me use a different color. This one here, okay? Now, is it total? 2, 1, 3, right? It is total. And then, is it functional? It is, right? Okay, easy to check. And surjective, A and B, right? A and B, good, awesome. So this is also good, okay? It's also total surjection. In case I'm going too fast for any option, please feel free to say. I can repeat, okay? Otherwise, I assume you're fine. Okay, number 3. This one here, okay? So let's say we got this one right here, okay? First of all, is it total? Not total. 2, 3 does not cover 1, 2, 3. Okay? Is it functional? It is, right? Good, thank you. Okay. And then surjective? Yes. Covers A and B. However, too bad, you fail one of them. Okay. Final one. Of course, if the question is only about yes or no, as soon as you find a failing property, you can just answer it's no. Okay. Okay, final one right here. Okay, final one. And is it total? 1, 2, 3. Yes, total. Is it functional? Correct. Okay. Is it surjective? No. Okay, good. Okay, awesome. But so far, I didn't really give you anything that's actually not functional, right? But of course, in the test, I might. But you know how to create a relation that's not functional. Okay. Okay, we got a bit more. Okay. How about bijective? Bijective, also, its definition is simple. You got to check to see it's actually total, injective, and surjective. All these 3. Okay, but of course, you got to know what injective really means and surjective really mean. Okay, all these 3. And let's now take a look at this one again. This guy here. Right? That's something we saw just a few minutes ago. Right? This guy here is the set of all possible bijection. All possible bijection. And we are saying that from 1 to 3 and AB, there's no way for you to make any bijection. And the justification is very similar to before, because you simply cannot really make any injective function from there. It's simply not possible, right? So the justification here is simply because no injective function can be made from these two sets, right? Why? You can look at the previous page for the justification, okay? And then let's see here. And we're also going to create a table shortly. How about this one here? Right? So now let's see if there's bijection, right? First of all, it's total. 1, 2, 3, and 1, 2, 3. And then is it injective? It is, right? A, B, C, right? Got the distinct values. And then is it surjective? A, B, C, right? A, B, C, that's good. This one's good, right? You can check both. And what about this one here? This one here, you can argue the similar way. This one is also a total, well, it's also a bijective function. You can argue that it's total, injective, surjective, right? I'll leave that to you. Let's draw a final table. Okay? Final table. Basically, in order to check to see whether it's a bijective function, so let's say this is number 1, number 2, number 3. Okay? 1, 2, and 3. All right? And then we got to check, first of all, it's a total function. So you got to be total and also functional. We check these two at the same time. It's a total function, first of all. Also, it's going to be an injective function. Also, it's going to be a surjective function. But if you like, you can actually split this into two columns to say it's both the total and also functional. Or we can do it at the same time. Okay, okay, for number 1. This one here. First of all, is it a total function? Cannot be, right? Because you can see 2, 3, and 4 only cover 2, 3, 4, but no 1, right? So here, it is not. Too bad. Is it injective? It is, because you can see distinct domain values. You also got distinct range value. Okay? Injective-wise, it is good. Surjective? A, B, C, A, B, C. Okay, good. But overall, it is not. Okay, number 2. Number 2, right here. Is it a total function? 1, 2, 3, 4, 1, 2, 3, 4. Also, it's functional. That's good. This one we can check. Injective. All right, because here 1A and 4A, distinct domain values, but got the same range value. Right? That's how you find a witness of violation. All right, so that one there, no. Surjective. A, B, C, awesome, covers everything, right? The range, good. This is good. Okay, final row. And then we have right here. Right here. So we got 1A and 2A. Is it a total function? 1, 2, 1, 2. Okay, it's also functional. Awesome. Is it injective? It is, right? Because distinct domain values, distinct range value, which is good. Awesome, thank you. Finally, is it surjective? No. A and C not covering A, B, and C, right? No. All right, good. All right, hopefully that's enough example for you to see. All right, I got a final one. Slide number 36 is just an additional modeling example. That one there, I don't think is going to impact how you're going to study for the test tomorrow. So that one there we can cover on Thursday. But if you want to look at that, that's okay. That one just about how you can formulate Java array using relation, which is a kind of interesting idea. But that one there, you don't need to worry for tomorrow's test. I don't think it's going to impact anything. But let me do one more example, okay? Bear with me, just one more, okay? And then we're done. More like a diagrammatic example, right? Just finish this one and then we're done. Okay, please. So we got X and Y over here. We got the first set and second set. Let's make the following assumption. Let's say the left set, X, is 1, 2, 3, 4. And also we got Y. which will be ABCD. All right, so we got these two. Okay, it's more like a visual example, right? Just finish that, okay, quickly. So this one here, obviously, is a bijection. Agree? Okay, it is total and also injective. You can see distinct domain values mapped to distinct range value. Also surjective because it covers all the range second set value, right? Good. So you can see one here is great. Partial is a functional. Total, injective, surjective. Of course, bijection is good because all these will check. Okay, 2, 3, and 4. Okay. First of all, is it partial? What would make it not partial diagrammatically? For example, if you got 1 maps to D and also B at the same time, that would not be functional, right? Okay, good. It is partial. Is it total? Yes, exactly. Yes. Oh, sorry. I was just confused myself. Yeah, exactly right. Yeah. It is no because you're missing 4. Yeah. Yeah, guys do listen. That's good. Okay. So you're missing 4. Is it injective? It is, right? Distinct domain value mapped to distinct range value. It is injective. Thank you. Surjective? No, because you're missing this one here, right? You're missing that. No, because you don't really have all the checks, so bijection is false. Okay, 2 more. Now, number 3 here, is it partial? This one here simply tells you that it's not injective. To be not partial, that means you got 3 maps to here and 3 maps to there. That will be not partial, right? Be careful, right? So partial is yes. Total is yes. 1, 2, 3, 4, right? And also injective, no. Because this one tells you that distinct domain values but map to the same range value. So not injective. This is important diagrammatically, right? So this would be a nice way to visualize. Surjective, yes, right? Because you got, oh, sorry, no. Because you only got B, C, and D. You're missing A. Okay? Yeah, you're missing A. All right, so that one is no. All right, so overall, you got no. Okay, number 4. Is it partial? It is partial, right? Because you don't have anything like that, right? So partial is yes. Is it total? No, because you're missing 4. And then, is it injective? No, because right here, this one tells you that it's not injective. Not injective. Is it surjective? Also no, because you don't really cover B. Right, so overall, also not bijective. All right, so let me say one more thing and then I'll let you go. So I think that the only slide we didn't cover is 36, which we'll do on Thursday. But that one there is not going to impact you much for tomorrow, so you don't need to worry. So I would say Thursday, we're going to finish that single slide on 36, and then we'll start with something new. Thank you so much. I'll see you in the Waiting Small Center tomorrow.